Hi, so for our E&M application project, Ken and I, Cassie, are doing magnetic pulse welding. For a little bit of background, magnetic pulse welding uses opposing magnetic forces generated by the metal to be welded and a coil to generate a strong magnetic force that pushes the outside piece of metal fast enough for two metal surfaces to form a metallic bond together. To give you some idea of the speed this happens at, the two metal materials to be welded collide at about 1,000 kilometers per hour, which is pretty fast. Some advantages for this is its really high production speed, as opposed to other forms of welding. It also has this ability to weld heat-resistant materials together because it's a cold weld that just uses forces to actually combine the pieces together. This can be used to join things like fuel pipes, fuel filters, exhaust system components, and other stuff like that.
So, alright, an example of a product for MPW are these MP systems by BMAX, which you can find on www.bmax.com, not sponsored, by the way. So you have to email them for specific product price series, product price in specific series. They have products that are capable of handling from 5 kilojoules to 2 megajoules, so the prices vary highly. There's also no price listed on Google, so only post-arc welders are listed for price, so it's difficult finding an actual number. But the potential costs for a coil is around, 2K, and they warrant at least 50,000 welds and up to 75K, which meant each weld costs about 4 cents. The machine itself is around 9 to 25K. These are estimations from the size of their capacitor bank. So a MP system with a capacitor bank of about 9 kilovolts to 25 kilovolts can cost around 15K, yes. Because I found that a 3-phase 15 kilovolts class pole mount outdoor capacitor bank for a typical utility distribution system is around $50K. So that's my guess. Also, this thing's invented in the late 1800s. I don't know how, but they exist, I guess. So I'm going to talk about the problem I faced while finding the datasheet. So there's actually no publicly available datasheet for a specific MPW machine on the entirety of Google. So I had to find the next best thing. So I found data comes from the analysis of thermomechanical simulation of a magnetic pulse welding process of the first experimental validations by AW and IG, and applications of magnetic pulse welding for aluminum alloys and SPCC metal sheet joints by TA, MK, and KO. I'll link it into the presentation for anyone who's interested. So before I explain the datasheet, I'll have to explain magnetic pulse welding. So basically, these are caveman terms explanations of magnetic pulse welding. So first, man plates two-plate coil, plate tube and coil. Coil move one plate/tube very fast. Plate tube smash into no move plate coil. Two-plate coil becomes one-plate coil. So here's a video that shows this. As you can see here, the top plate collides with the bottom plate, and they basically form a bond. Yeah, pretty cool. So now we're going to get into the analysis of the datasheet. So here we have the component listed for each of the material we have. And then we have the electroconductivity, specific heat capacity, mass density, and thermoconductivity of the said material. So the materials involved are stainless steel, aluminum, and copper. The stainless steel serves as a parent plate, providing structural integrity and stability. Aluminum, acting as the flyer plate, plays a significant role in the collision and subsequent bonding due to its lightweight and malleable properties. So basically, aluminum is the thing that flies into the steel plate as seen in the previous video. Additionally, the coil, a fundamental component of the welding process, is crafted from copper, known for its excellent electrical conductivity. The table showcases the two copper properties like electrical conductivity, specific heat capacity, mass density, and thermoconductivity, which are essential to determine the behavior and performance of these materials during the welding process. An important thing to notice is the difference between electroconductivity between a stainless steel and aluminum. Since the stainless steel is the parent plate, the electrical conductivity has to be less than aluminum in order to maximize the velocity in which the parent flyer plate flies into the parent plate. Yeah. Now we're going to take a look at the electromagnetism details. The principle of electromagnetism for magnetic pulse welding, which I'll be referring to MTW as MPW from now on, is the rapid discharge of a high capacitance electrical pulse through a coil, which generates a strong electromagnetic force, which results in a powerful magnetic field, and in which this said magnetic field induces eddy currents in the top plate positioned above the coil. The top plate is the flyer plate in this case, which flies into the bottom plate. The interaction between magnetic field and the eddy current generates intense magnetic pressure, causing the two workpieces to collide and bond at their interface or collision point. Now, I'm going to call the caveman to explain why these plates and coils move. So first, capacitor bank discharges, in which a big current in the coil make a big magnetic field around the coil, and then big magnetic field make eddy current in plate or tube, in which eddy current plus magnetic field equals big force. Big force move plate or tube. Plate slash coil smash. These are tubes. And two plate slash tube, now one plate slash tube. So I can see, as you can see on the top images, the aluminum part flied down into the parent plate, which is actually copper in this case. As you can see, they were bent around the original shape of the parent tube the flyer plate had. And they used to be originally straight, but after these magnetic pulses, they became bent into and flew into the parent plate and now form the cold weld. So I will now have to explain this electromagnetic details, which the diagram on the right. So the main E&M components are pulsed power generator consisted of a simple inductor with low inductance, a bunch of capacitors with high capacitance, as well as a wire with direct acting inductors in order to allow the current to flow through the coil to induce a magnetic field and create an eddy current in the flyer plate. So a typical value for a current magnetic field and Weil-Zeiss coil loops are for a formation of a very simple and small solid state cold weld is around 1.4 kilojoules stored in discharge in capacitors, which generates a 20 Tesla magnetic field. And this will lead to a 150 kiloamperes at 1.4 kilojoules capacitor energy discharge. This 150 kiloamperes is the peak current throughout the magnetic pulse welding and the highest pulse, which leads to a collision speed of around 400 to 500 meters per second of the top flyer plate into the parent plate. So now here's another diagram, in case if you didn't understand the last one. We have these coils around here, which creates a magnetic force in the outer tube to fly into the inner tube, which creates a cold metal weld because they run into each other so fast. And here's a simplified circuit in order to understand how the circuit works, I suppose. So one thing to know that during the discharge of the magnetic pulse, the energy is actually discharged in a reducing sine wave. This is a current waveform at 9 kilojoules discharge energy, which I think is pretty cool to see. And as you can see in this diagram, the most important takeaway is the simple image on the right, which is a magnifying of a interface in which the magnetic pulse weld or the cold weld was formed. The weld resembles a wave that blends into the top and bottom material, which I think is pretty cool. And here's another demonstration of this wave-like texture in another, what's it called? It's a plate magnetic pulse welded together. Yeah.
Now, there are some limitations that come with magnetic pulse welding. First, it's challenging for welds that are not roughly circular, so the geometry of the parts may have to be modified in order to be welded. It's also an expensive investment to make. For something that manufactures at a lower volume as opposed to being mass-produced, that initial investment may not be worth it. Some weaker, more brittle materials may also crack. The process of this weld requires a big amount of force to be applied to the pieces that are to be welded. Under this extreme pressure, a weaker material may crack where the weld happens. The surfaces to be welded also need to be overlapping each other. Since magnetic pulse welding pushes two pieces of metal together, they can't be adjacent and level, they have to be overlapping in some way. Lastly, the material also needs a good electrical conductivity. The magnitude of the eddy current in the metal to be welded changes based on the conductivity of the metal. A less conductive metal means a weaker eddy current, which then produces a weaker magnetic field. Therefore, the metal that will be pushed into the other metal needs to have a certain electrical conductivity for this weld to work. However, there is actually a way to bypass this limitation. If you have a piece of metal, maybe some like stainless steel metal that is not as conductive, and you want to use that in the weld, you can actually wrap a more conductive material around that, for example, a sheet of copper, and then the weld would actually work. And that's it. So thanks for watching and listening.